we are going to finish our journey in Chapter 2 by looking at protic and aprotic solvents. And then, because we've talked so much about solubility, we are going to also look at the fourth type of biomolecule fats. And so that's how we'll finish Chapter 2. So what we learned in section 2.7 was that ionic compounds have a very high solubility in polar solvents like water. And so you can see we have an ionic compound here, and it breaks up into its ions, okay? And so in water, the solubility of sodium chloride is 35 grams, okay? And this high solubility is due to that really strong solvation that we talked about due to those ion-dipole interactions. Now, the magnitude of water's dipole is about 1.9, okay? I want us to look at the solubility of sodium chloride in another solvent which is called DMSO. And DMSO, the solubility of sodium chloride is only 0.4 grams. Now, DMSO is a polar solvent, and it's got a greater dipole than water does. See, it's got 4 divides there, so it's almost double what water has. And so the question that we have here is, and that we need to think about is, if intermolecular forces and entropy were the only things involved in solubility, then why is there so much sodium chloride that can dissolve in water, but not very much sodium chloride can dissolve in DMSO, which is a polar solvent? So there have to be other things that are at play here. So the other thing that is at play is that it's not just that the partial positive charges are there. It's also important to consider how close the partial charges are I didn't tell what the partial charges. Let's say the partial charges of the polar solvent molecules can get to the ions. Okay, so when we look at this, let's look at the next image, which is an illustration of what we're talking about. So here is sodium chloride, and what you can see here is with sodium, here's where the water molecules are, and with chlorine, here's where the water molecules are here. Now, if we look at DMSO, which is also, again, a polar solvent, what you're going to notice is you can't get as many solvent molecules around the sodium or the chlorine. And so what that means is the solvation of these ions is not as strong in DMSO as it is in water. This obstruction is really due to the bulkiness of the methyl groups. And the methyl groups here on the DMSO see the methyl groups right here, they keep other molecules from getting close, and that's a problem. Whenever we run into something in organic chemistry where we have a problem where bulkiness prevents a reaction, that's called steric hindrance. And so what we find here is that just due to size, we are not, and this isn't a chemical reaction, but due to size, we don't get as good a solvation. So because we don't get as good a solvation, there can't be as many ion-dipole interactions, and not as much sodium chloride can dissolve. Now, water, and what we can do is we can divide kind of our solvents here, our polar solvents, into 2 categories. And so water is an example of something called a protic solvent, And then DMSO is called an aprotic solvent. Now this gives me the biggest headache in the world, right? Because here we go. Protic solvent is water. Aprotic solvent is like DMSO. So we've really got to watch where we put that A. And so we'll try really hard to enunciate there. When we look at this, here are some common polar protic solvents. Here are some common polar aprotic solvents. What I want you to notice is that polar protic solvents tend to solvate both cations and anions very strongly, right? So these guys solvate both cations and anions very strongly. So polar aprotic solvents, on the other hand, solvent cations pretty good. So they solvent cations very strongly, but do not strongly solvate anions. Okay, so there's a big difference there. Sorry, I had to pause because there was one other thing I wanted to say and I got lost in my notes. The way that we can distinguish a protic solvent from an aprotic solvent, and it's right here, which is kind of why I lost it, because I typed it out for you, is that a protic solvent is going to possess a hydrogen bond donor, whereas aprotic solvents don't. And so protic solvents have hydrogen bonding, aprotic solvents do not have hydrogen bonding. And that leads to why they can solvate the cations very strongly, but not necessarily the anions. And so that's something we see there. We're going to talk more about protic and aprotic solvents later. What I really want you to be able to do here is understand a few things. I want you to be able to identify protic and aprotic solvents, and based on the fact that protic solvents can possess hydrogen bonds and aprotic solvents don't possess hydrogen bonds. But like I said, in Chapter 9, we're going to go back and see how this affects some reactivity, but we don't have to necessarily worry about it right now. We're going to finish the chapter talking about lipids. Lipids are the fourth class of biomolecules, and these are the ones that are characterized by their solubility. Most of our lipids are going to be nonpolar hydrophilic compounds, so that means they're relatively insoluble in water, and they can be divided into kind of four subclasses. So the first subclass is fats. The second subclass is phospholipids. The third subclass is steroids. And then the fourth class is waxes. Okay. So one type of lipid, as I mentioned, is a wax. You see I have a friendly bee here, so you may be familiar with beeswax, for example. And so we can see that is a bee. Now, different books say different things, and your book is going to say fats can be of animal or plant origin. Most books make a distinction here and say fats come from animals and oils come from plants. And that's a distinction I want you to kind of be aware of, because, and I'm not sure why the book didn't make this distinction, because every other book that I've ever had does. But basically what we say is, look, fats, right, are solids at room temperature and they come from animals. Plants are liquids at room temperature and we call those oils. And the most common biological function here is going to be storage. So fats contain fatty acids that are going to help regulate blood pressure and blood lipid levels and play major roles in inflammatory responses to energies. They also have a variety of other functions. So they are going to help protect organisms for foreign substances, either chemical or biological, by temporarily locking them away in new fat tissue. Now, when we talk about fatty acids here, right? These are just long chain carboxylic acids, right? And when we look at these long chain carboxylic acids, we're going to notice here, right, there's the long chain, and then we've got the carboxylic acids there. You can see here we have these are some common fatty acids that we run into. All natural fatty acids are going to have an even number of carbons, because in nature fatty acids are synthesized from acetyl coenzyme A, which is also called acetyl-CoA, and that's a 2-carbon atom source. And then most fatty acids, I'm going to abbreviate fatty acids as FA. Most fatty acids have between 12 and 18 carbons. Okay. Although they can have as few as 4 and as many as 22, this is where what we commonly see in nature. You can have saturated fatty acids. These fatty acids in their carbon chain only have single bonds. You can have mono unsaturated fatty acids. And these guys are going to have 1 double bond. And then you can also have polyunsaturated fatty acids. And these have more than 1 double bond. So, for example, these are saturated fatty acids, lauric, palmitic, and stearic acid. Oleic acid is a monounsaturated fatty acid because it has 1 double bond. And then linoleic acid and linolenic acid have multiple double bonds. And so they are going to be polyunsaturated fatty acids. Another type of fat that we're going to run into are triglycerides. Triglycerides are also sometimes called triacylglycerols. And so right? But we most often see them as triglycerides. If you go and get your blood work done at the doctor, they're going to measure your triglycerides, right? Because if you have a lot of triglycerides, that's indicative of heart disease. I want you to look at how triglycerides form. You're going to see here in red, there's a glycerol molecule. And then we have 3 fatty acids. Now, here are the carbon chains. They can be the same or they can be different. This is just a way to store our fatty acids. And then what happens here is you have a bond that forms between the OH of the glycerol and the OH of the carboxylic acid. When this forms, you get a new functional group. This is an ester functional group. And you also form 3 water molecules. Now, you can also have phospholipids. Now, phospholipids look really similar to triglycerides with the exception that they have a phosphate group. They also consist of a glycerol backbone attached to 2 fatty acids via these ester linkages. So the big difference here, there in red is still your glycerol backbone, but now we have a phosphate group. And then we have these 2 fatty acids. And that sometimes is called a diglyceride because it has 2 fatty acids. Typically what we see here is the phosphate group is bonded to the second molecular fragment, right? So like a choline fragment, it'll be bonded to another thing here. So, and then it'll be specific. So what I'm saying is this is generic. Notice there's a molecule here. this is a specific phospholipid. It's called phosphatidylcholine. And that's because here at the phosphate, there is another molecule that is a choline molecule that is attached. You've probably seen this in biology because there are two different types of polarity in this molecule. This is an ionic head group. It's going to have a positive and negative charge. And because of this positive and negative charge, it can associate with water. But here with these long hydrocarbon tails, this is hydrophobic, and so it associates with oil. And so cartoon-wise, it's shown a lot of times like this because it also makes up cell membranes. So if you've seen this cartoon in biology, this is the molecule that you're looking at, and there's a reason there's two different polarities here. So as I mentioned, right, we have those two different polarities. And so you can see that here, and it forms a lipid bilayer. So phospholipids are pretty structurally similar to fats and oils, and so that means they can also pretty efficiently store energy too. The reason though, so fats and oils don't necessarily make up the cell membrane. Phospholipids do that. And so the reason they're special and can make up the cell membrane is because of these vastly different properties that we talked about. Here's the phosphate portion, which is ionic, right? And so it can interact with an aqueous environment. Here's the other phosphate portion. And then here's the fatty acid portion, which is nonpolar. Now, this is called a lipid bilayer. So bi means two. There are two layers here. And what you're going to see are the things that are nonpolar interacting through London dispersion forces, while the polar head here that's ionic can interact through ion dipole interactions. Now, the cell membrane's hydrophobic interior and hydrophilic exterior are critical because they are going to restrict the free passage of most molecules from one side of the membrane to another. Hydrophobic molecules, such as cholesterol, are going to also reside in the membrane's interior, right? And so we can see here, this is a more, this is a picture of the cell membrane with things embedded, right, in the lipid bilayer. And so here's cholesterol. Cholesterol is a nonpolar molecule. It's going to hang out right here in the cell membrane. It helps control fluidity of the membrane. So you'll learn more about that in biochemistry, right? And then we have hydrophilic molecules like carbohydrates, like your ABO blood markers, which are hanging out on the surface. You can also have glycolipids, right, which are lipids with some carbohydrates that are associated with them. You can see here there are proteins, there are integral proteins and transmembrane proteins that stretch from one side of the cell membrane to the other. The cell membrane is really super interesting. The molecules that make it up are super interesting. I sit here before you and say, oh, we've got these 4 categories. But what you're going to find when you get to biochem is there's some molecules that are kind of hybrids of both categories, like glycolipids or glycoproteins, right? So this is a protein, but this has some of the sugar markers on it. So lots of kind of fun things that you get to learn in biochemistry as far as the function of molecules are concerned. Let's talk about steroids too. So steroids have a wide variety of biological functions. They are some common things that we've heard of before, like cholesterol. They serve as sex hormones, testosterone and estrogen. They regulate blood pressure, and they treat inflammatory conditions through cortisone. You can identify a steroid because it's going to have the same basic ring structure. It's going to have 3 cyclohexane rings in this exact formation, A, B, and C, and then a cyclopentane ring here in D. That's the exact same formation. So let's look at some examples of steroids. So here's some of the steroids that I mentioned on the previous slide, and I want you to notice the ring structures that are common here. So Notice though that like all these have cyclohexane, 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 cyclopentane, but notice that we can have some double bonds, right, that pop up. Notice that we can have different groups and functional groups that are off of these rings. But what classifies these as a steroid is this ring structure. Now, the very last lipid that we're going to talk about are waxes. Here are some examples of waxes here. Waxes are just secretions from plants and animals that are solid at room temperature, right? They tend to melt at low temperatures. Right? They're generally pretty soft and malleable, so they can be formed, and they're very, very hydrophobic. And it's generally used as a protective coating in nature. So, for example, there's a wax that will coat leaves if you're really interested in that. You can see earwax here. You can see there's beeswax. Wool has a coat of lanolin, which can help shed water. So lots of different places that we see waxes. Now, the principal component of beeswax is this molecule here. It is called tetracosyl hexadecanoate. All right. And basically what you're going to see with waxes is that they have two really long R groups on either side with an ester linkage in between. Right. And so that's what we're going to see as far as waxes are concerned. Well, we have finished our review of general chemistry, talking mostly about intermolecular forces and how they affect melting points, boiling points, and solubility. We talked about different solvents as well as waxes in this chapter. And so this for us concludes chapter 2.